So the sequence of perfect squares are the same from the ancient Greeks when they realized that you could arrange squares using these dot formations here. So I added these numbers, but if I didn't add those numbers, how would you figure out a sequence S of n that denotes the nth square number for this? What do you guys think?
What page is this?
43.
Thank you. Oh, back to this thing.
All right. So what do we think, guys? How would we make a formula for this? Tom, go ahead.
I mean, I would. Well, I mean, first you gotta find out what's in the first column.
So that's a good point. So you're talking about like a table?
Yeah.
All right. So let's make a table for this. Okay. So our first column would be. I put X and Y there. Is that okay for you guys? For
A and B.
So X and then Y. So what are our X's here, Tom?
Oh, your X. Well, first would be one, then you got 4.
So that I think you're giving me my Y. I'm just talking about my terms in the sequence,
yeah.
right? So let's say it's N. If it was N.
It just goes by greater
Right.
ones.
So 2, 3,
Yeah, like
4.
regular
Okay, and then what is my Y or my S of N?
So you start out with your first one, which would be 1.
Okay. How do we know that, other than the fact that I wrote that number there?
Well, there's 1 there.
Okay, what about the next one?
That'd be 4.
And then talk to me about that picture and why that makes sense.
All right. So first, look at the first column within the square per se.
Okay.
And you can see you can count down by ones to get how many are in the.
Okay, so you're saying there's 1, 2, 3, 4 dots?
Yes. Like
Okay.
if you look at each side, they have a certain amount.
Okay. So what about this next one for 3?
Next one, see how many are on one side.
Okay, so there's 1, 2, 3.
Then go on the other side. Like go down.
1, 2, 3. And
Multiply 'em,
multiply them, and you
9.
get. All right. So it sounds like you know where we're going with our formula. So what did you just do? What's our formula then for S of n? S of n. If these are our n's, 1, 2, 3, 4. How do I get my y's? Sequence. It can be just anything. Squares, we can say. So you just did it. How did you get each of these y's? What did you do with the x to get your y? What did you multiply here?
Multiply by itself.
Okay, but what by what?
2 by 2.
Okay, and then here by what?
3 by 3.
And then this one?
4 by 4.
So what are you doing?
Well, I'm squaring basically.
Yep, you're squaring. And you're squaring the what? The sequence number, right? So S of n equals n squared, right? Okay, so that's a little different than what we've been doing. We've been doing geometric and arithmetic. Anybody know what type of function this is?
Exponential.
Not quite.
Quadratic.
Quadratic, right? And then that's something that we haven't actually got over, so that's pretty good that you guys got that. All right, so we have the sequence here, S of n squared. So let's prove whether or not 169 is a perfect square. How do you think we're going to do that?
All this stuff.
You do
All about David, what do you think?
13 squared in the calculator.
13 squared in the calculator. Well, how did you talk to me how you got to that point? How did you know to do that?
Square root of 169.
So he did the square root of 169 and he got 13, right? Okay, so how do we know using this sequence here? How do we know that 13? I mean that 169 is perfect square. Use this the way that they've graphed this out. What would it look like? That 169.
13 by 13 squared.
Perfect. So it would be a 13 dots going this way and 13 dots going this way, and that would be 169 dots, right? Okay. So then what about this number 200 here? Let's see whether this is a perfect square. How do we figure that out? Juliet, go ahead. All right. What is the square root of 200?
No.
What is it? I got something a little different. Anybody got something different?
I got
Darlene?
14.14213
Okay, that's good. So 14.12. So why isn't that a perfect square if I can get that 14.12?
It's not a whole number.
So it's a decimal. So what you guys seem to be saying, right, is that I can't have a decimal because of these pictures. Because you can't have part of a circle, right? If we're dealing in these circles, how can I have 14.1? I don't know how to do 0.1 of a circle, right? Okay, so that seems to be a restriction that we have here. Okay, so then what about this? If S of n is 225, what is our n?
15.
15, right? Because
Oh, I remember this.
Yeah, there's a number.
okay. So yeah, so then and then finally, so what would that? So Stephen, what would that square look like?
15 down.
15 dots down, 15 dots across. Okay, and then finally, which term is number 400 in the sequence of perfect squares, and how would you figure that out? So which term is the number 400, Rachel? 20. And how do you figure that out? So so you square root it, so you know that it's the 20th term. What would that look like in that picture sequence? What would it look like? 400. 20 by 20. Okay, so what are we doing here? What are we going up by each time? What is this set? What is this set of x's? How would you describe them? Can't be decimals, right?
Real numbers,
You said
whole numbers.
Whole numbers, right? So basically, what we're saying here is that this function only works with whole numbers. Okay, so keep that in mind as we go forward. All right. So now so now we have the same sequence, right? What does S of 50 mean, Stephen? If I am using the same sequence, what does S of 50 mean?
Is it asking you for the 50th term in the sequence?
So the 50th term of the sequence. So what do you think that square would look like?
50 by 50.
50 by 50. Okay. What about S of 0, Stephen? What would that look like?
Well, is 0 the first term in this or no?
Well, if this is S of 50 means 50 by 50,
So
right?
no.
What would S of 0 look like?
Nothing by nothing.
Nothing by nothing. Is that possible?
No.
No. Okay, so that doesn't really work either, right? Okay, what about S of pi?
Well, that's that wouldn't work.
That wouldn't work,
Yeah.
right? No, that's a 3.14. So we can't use either of those terms, right?
Not that one either.
What else? Why can't I use negative 1?
You can't have less of something if there's
Can I have how do you draw a negative dot?
You can't.
You can't, right? It doesn't make any sense. Okay, and 2.4,
No.
can't do it. Okay, so what we've done here, what do we kind of done here? We've put a restriction on what we can plug into this function, right? So what is that restriction?
Whole number.
Whole number. That.
What? Whole numbers, very good. Okay, so now let's look at a very similar function. It is a formula for the area of a square where each side of the square is x. What do you think the area? What is the Lulu? What's the formula for this? What's the area of a square if both sides are x? How do you get the area of a square? X squared, right? So this is x squared. So this is just the same as our dots, right? Exactly the same? Okay, let's see. So what do you guys think the area of the square is if our side lengths are 3 centimeters?
9 centimeters.
9 centimeters squared, right?
Yep.
Okay, what about 10.5 centimeters?
20.25.
110.
No, never mind.
110.25. But wait a minute. You guys said before I couldn't use decimals.
But it's measurements.
This is
centimeters.
But it's a measurement, so there's different rules apply. Different context, different situation, different rules. Okay. What about if the sides were pi? What would? And you don't need to give me the exact number, but what would my area be?
No.
Just think of pi as a variable. Pi squared, right? Sorry, that was a misleading way to ask that. But so I'm able to do 10.5 and pi here. Why? Why am I able to do that with this one? Why can measurements be? Why don't measurements have to be a whole number?
Because you can have decimal.
Right, you can have half centimeter. We measure that stuff all the time, right? If you're measuring a fence, you're not going to only do whole numbers. If it's a half of a foot, you're going to go with a half of a foot, right?
Yes.
Okay, so Una, what does a of 0 mean in this sense? If the area is x squared, what does a of 0 mean? So if I had a go ahead.
Shape.
It's not. It doesn't. You can't. it can't happen, right?
Yeah.
So why wouldn't it make sense if I had a
Because then it
fence
would-
with both sides of my fence that were squared in were 0 feet long?
Wasn't a fence.
Exactly. No, it's not a trick question. It's not a
Okay.
fence, right? That doesn't make any sense in this context. Okay, so that seems to be a rule. So we expanded our set of inputs that were allowed. Now we can use decimals, we can use pi, but we still have some rules, right? We can't use 0. What about a of -10?
Then both the sides are -10.
You can't have a negative foot fence, right?
Also not a fence.
Also not a fence. Okay, so that doesn't really make sense. And then they have here they're trying to trick you, a of square root of 2. Can we have that?
Mm-mm.
Yes.
Yes. Why?
Just
Because
kidding.
it's like 1.41 and you
Right.
got one.
And you can have 1.41s, right? So that's just it's just to say, hey, it's not just everything that looks different. You got to think about what you're being given. Square root of 2 is a number that could work, right? Okay, so what's the point of why are we doing all this, Mr. Pacheco? All right. So the point is that with different functions, we have different allowable inputs. We have different pieces that we can plug in, and then in order to get our outputs. And it depends on the context. It also depends on the definition that you're given. So those were situations. Those were a fence or a perfect square. But you might just get an algebraic function, and in that case, somebody might just say x can't be this, and that is the same type of situation. So for every function, you guys want to write this down. For every function, there are certain inputs that make sense or are true, and others that do not, and they're false. As a set, the inputs that are true are called a domain. So a domain is the inputs that I can enter into my function to get a true answer. So in my first situation with my dots, what was my domain there? In this first slide, when I had these perfect square dot squares, what was my domain? Somebody?
Whole number.
Whole numbers, right? Because that's all that was permissible for me to plug into this equation was whole numbers. That's my domain. That's the domain that I'm working with, right? Okay, so what about with this this square situation, Heather?
Oh.
What was my domain here? What was
Wait,
what
can I
was
see the definition again? Because I didn't get to write it
Sure.
down.
Sorry, that's fine.
That's what-
All right, so if I have a square,
The domain. Wait, so the domain was possible numbers that like weren't.
domain is any inputs that can be true.
Yeah.
Any inputs that make sense for this situation. I have a square that have a centimeter long sides. What's my domain? That's okay. Anybody else think they know what the domain is here? Ben.
Whole or just numbers that are not 0 and negative.
So numbers that are not 0 or negative, so positive numbers, right? So any number that makes sense when you're measuring a square, which in other words is non-negative numbers and not 0, right? So that's what we were able to determine. So the domain here is still restricted. We can't put anything in there. We can't put a negative number, but it's not the same as the last situation, even though the functions were very similar, right? So hopefully what you guys are getting out of this is that domains can be very loose. You can be any number. You can have very strict domains where it's just whole numbers, or maybe it's just only whole numbers from 0 to 10, or we can have somewhere in the middle. It's any positive number, any positive real number, but it can't be 0, it can't be negative, right? So that's somewhere in the middle, right? So that's what a domain is. Okay.